All right. So the units that we are looking at the LOD in match those of the background equivalent concentrations. And the background equivalent concentrations are in milligrams per liter, but you can see that our limit of detections are pretty low. So milligrams per liter is not a great unit of measure for the LOD. I would suggest using micrograms per liter, which is parts per billion. So all that you would do is what? To convert milligrams per liter to micrograms per liter. Or instead of dividing, multiply by 1,000, right? Because we're going from parts per million to parts per billion, right? And so if you multiply that by 1,000, then you'll get about 0.50 for cadmium, and for lead, it's a little bit higher, 0.97, right? Parts per billion, it's pretty low. Okay. Questions about that business? So the other stuff, I'll just, I'm not gonna calculate it with you because you can do that. But if we look at the data, right, each data set has a replicate, a 2 times dilution. Replicate is checking for precision, dilution is checking for accuracy, and then a CCV, right? And for the replicate, what I have here in column B is that we're replicating sample 10, right? So the original measure of sample 10 is on the row that says sample number 10, and the concentration is here. So for the first time we measured sample 10, we got 1.243. The second time we measured it, we got 1.269. And we just calculate percent relative difference, right, to get precision. For the dilution, right, when we diluted the sample 2 times, we got 0.673. The original measure of it was up above, right, where it says sample number 12, and that was 1.051. So in order to calculate, right, the recovery of our diluted sample, we take that value, multiply it by the dilution factor, which is 2, and divide by the original, right, the undiluted sample, right, 1.051. Okay. For CCV, you know how to do that. The CCV known was 5. The CCV measured was 4.738. So it's just measured divided by known times 100%. And that's no problem for you, right? So that would be done for each of these sets. So all of our sample analyses were bracketed like 3 times in 3 different sets. Okay. And always the very last thing that you do in any analysis is quality control, right? Because if you don't finish off with quality control, then you don't know what your last samples were in terms of their precision and accuracy, right? So you got to know that. So we'll move on from here, and we're going to go to the next worksheet, which is process data, no QC. So process data, no QC is all the data now. Column F here is the equilibrium solution concentration, which is CEQ, and then I've just added the mass, the soil masses that you recorded. For the next one, Los Osos BTSS, this is just a worksheet that is going to enable us to convert CEQ here in milligrams per liter to millimoles per liter, because I want to represent our data in terms of on a molar basis instead of a mass basis. And the reason why we're going to do that is because the comparison between metals is more straightforward, and you're comparing moles to moles than mass to mass. Okay. And then from our equilibrium solution concentration and our starting concentration, which is in column D, the difference between those two will allow us to know what the sorb quantity was, which is which variable. And your choices are CEQ or Q, right? Okay, so we have the same bit of data for Holland, right? So I just broke it up in terms of Los Osos BTSS and Holland BT. Okay, and then there's some further transformations and calculations that are done, but let's go to the bottom of the Los Osos BTSS worksheet. And in the bottom of the Los Osos BTSS worksheet, we have all of our blanks. So what we have here are all the no soil blanks, okay, for cadmium and lead. And I just grouped them all together. So the method detection limit is going to be the same for both of them, right? Because we got the, well, is that right? I don't think that should be right, actually. All right, there's a problem that we need to fix and adjust here. So what I like you to do is the values that we want down here for cadmium in that column should correlate with the no soil blank quantities on the ICP. So it should be those ones. And it should be, oh, we got a problem. Should be those ones there. But also I included what's on the next spreadsheet. On this one, I think. Yeah, the Holland BT. Where we got these ones here, and those ones there. Oh, wait. That's cadmium. Do you see the problem? No. The first six. So here, these ones here.
No, the no soil, the first three no soil blanks, and the second three no soil.
No soil blanks.
Match the first six.
Yeah. But yeah, that's right. Here's the problem, though, and I didn't catch it the first time that we did this. The problem is that we didn't analyze cadmium here, right? We measured lead. So these blanks are the lead quantity. You see what I mean there? All right, so let's fix that. And so the way that we're going to fix that is we can do like, we could put in a formula there, but it's probably just as easy to take these three values here. They're already there, but I'm just going to copy these and paste them down here for cadmium. Like that. Okay. Why is it doing that? Clear that out. Okay. So what I'd say is like clear out those formulas there, but not the average and the standard deviation. Just delete it. And then take your cadmium no soil blanks for Los Osos BTSS, copy those and paste them down here for the cadmium blank. Thank you, Elijah. Right, do a paste special. Yeah, thanks to Elijah. We're gonna do a paste special. So, and it's gonna do paste values, which is what I want to do. And these for Los Osos BTSS lead, those need to go into the lead column. Let's do a paste special. And then we need to go to the Holland BT worksheet and do the same thing, right? So we're only taking these three cadmium ones, Holland cadmium, and we're going to paste them back just below special. There we go. Funny. And then for lead, we're going to do the same thing. I apologize for my mistake. So it'll still calculate an average, it'll still calculate a standard deviation, but then we need to calculate a method detection limit, which we'll do together in just a moment. Are you good or are you confused? You're good? Yeah. All right. So method detection limit is the mean of our blank analyses plus the standard deviation of our blanks times the t-test, student t-test alpha of 0.01. So we have our mean, we have our standard deviation. How do we get our student t-test? Go to the table, or you can just go to the internet and put in student t-test, one-tailed. It's a one-tailed student t-test. I think I have it too, but go ahead and look it up and see if you can find what it's supposed to be. Two 0.16, 0.15, yeah. All right, you got it. What is or what should be your student t-test value? What is it? Hugo. No, why not? Sample size. How many? We usually do 10 blanks. This time, how many do we have? No. No. You're just making up numbers. It's not a good way to do it. So 6 samples, degrees of freedom is n-1. 3.365.
3 was close.
What was that? 3 was close. 365 is our t-test value. So then just create a formula where you calculate your method detection limit. All right. So if you did it correctly, you should, and if I did it correctly, should have a cadmium method detection limit of 0.06 milligrams per liter and a lead detection limit of 0.23 milligrams per liter, that is the lowest level that we can say with a 99% confidence that those values are actually different than blank. Right? Yeah.
Yeah.
Good. So then what we got to do is go up to our data, keeping in mind that cadmium is 0.06 and lead is 0.23, and look at our data here. So here's cadmium data here. And any of those values that are less than 0.06, because we're doing some manipulations and calculations with these data, we're going to call them 0. Okay. Basically that nothing is there that we can measure. So I'm going to change all these to zeros. And then for the lead stuff, I got to do the same thing, right? So my detection limit is 0.23. Yeah, 0.23. So I'm going to do the same thing for my lead data. Anything that's below 0.23, I'm going to omit from the data set. You do have one value that is right on 0.23. And what I'd like you to do for that one, that is column or row 38. It's F38. You see that one right there? F38. Just delete it and don't add it. Don't call it 0. And the reason why we're going to delete that one and treat it differently than the others is because that's not a blank, right? And we just have poor precision for this value here. So I'm just going to just not put anything in there and delete it, but everything else, I'm just going to make it 0.
Those ones also not blanks.
They are. They are not blanks. What's the difference? I asked, what's the difference? So the difference is that like these whole data sets, right, are bracketed in 3s basically, right? So we have 3 no soil blanks. We have 3 soil blanks, 3 samples where we added 0.25 millimoles per liter of lead nitrate. And then we have 3 samples where we added 0.05 millimoles per liter of lead nitrate. And one of those samples is below 0.23 or was right on 0.23, and the other 2 were above 0.23. My assumption is that that 0.23 is an outlier. And so I'm just going to exclude it from the data set. All right. And here's why, is because the other two values that we have, one, there's poor precision in them, and also they're more than double or about double what that concentration was that we removed. Okay. So I feel fine about that. Tony does not feel fine about it, though, I don't think. Do you, Tony?
I guess.
All right. So let's do the same thing for the Holland BT data. Anything for cadmium that's below or equal to 0.06, call it 0. And anything for lead that's below 0.23, call it 0 also. So for the Holland BT, right, your first data that are above our detection limit should start at 2.46. For Holland cadmium, the 0.1 millimolar addition. And for lead in that soil, it should be the one that's 0.25 millimolar addition. It should be 0.71. All right. All right. So let's go back to Los Osos BTSS. So what we got to do now is convert milligrams per liter to column I millimoles per liter. That's pretty straightforward calculation. But let's talk about how to do that. Yeah, and then just don't forget to do it in the Holland BT also. Yep. So just fill that formula down. Totally can. All right, so now you got the equilibrium concentration of lead and cadmium in both soils, or CEQ. And what we want to calculate now is Q, right? That's the last calculation that we do before we break. So I'm going to start with my Los Osos BTSS spreadsheet. And the way that we do this is we have the concentration that we started with. So we got the original quantity of cadmium or lead in millimoles of cadmium per liter. And we're going to subtract from that our equilibrium, right? Or is it okay if I just write CEQ, right? In millimoles per liter. Right? And then we need to convert that value to millimoles per kilogram. Right? We got to take that and convert it to millimoles per kilogram of soil. How? How in the world will we do that? This is F2, that's pi 2. Okay. Soil to solution ratio, right? Like Shannon says, always soil to solution ratio. So what was the volume of solution that we used? And we just make it up, right? Like Hugo does, we use 2 samples or 4 samples or 6 samples. But I'm just kidding, right? Yeah, of course. How do you know what the volume was? Right, but what's the volume of solution that we use, and how do you know? What? 30, and how did you know? It's in the procedures, right? It's in your lab notebook. Okay, so we used 30 milliliters, and we used approximately 1 gram, right? So the volume or the mass is in column or cell E2. But anyway, we need mass on the bottom. So it's about 1 gram, or that's column or cell E2. And this is 30 milliliters. And we just need to make our units match, right? But you'll see that they're going to cancel out anyway. Right, so we got 1,000 milliliters per liter. That cancels. That's going to cancel with those. And then grams per kilogram, same 1,000 grams per kilogram. Grams cancel and thousands cancel. Okay. So all you got to do is you plug in that in your formula, multiply that by 30 and divide by E2. And then do that on both spreadsheets. And when you're done with that, we'll take a break until 1:20. And so put F2 in, yeah, in parentheses. Well, you want it to follow the proper order of operation. And if you don't do that, yeah, I did it wrong. Sorry. It's not F2. Right, what is it? It's D2. D2. Thanks for catching that. It's D2, right? D2 is the original concentration that we started with. It's D2 minus I2 and times 30. Divided by E2. Just drag that down. And you're going to get some hashtag value, right? Do any of you ever hashtag value? I'm Elijah. Hashtag value. Yeah, come on. Let's do it. All right, so do it in Holland BT also. If you did it right, right, in your Los Osos BTSS, the last value for cadmium will be 54.0179, and the last value for lead in Los Osos BTSS will be 109, a 0.1383. And for Holland, right, it'll be 22.7455, and for lead, it'll be 38.4425. If you did that right. So the next spreadsheet, cadmium and lead, just consolidates all the information into a couple different worksheets or a couple different sections. And it, since everything is done in triplicate, it calculates an average and a standard deviation. We could have had JMP do this pretty easily also, but I just figured I'd do it here so it would save us some time from jumping between programs. And then for the sorption isotherm data, which is the next one, it just puts everything together for the averages are in the top one and the standard deviations are in the bottom one. And the reason why I included standard deviations is in case we wanted to plot some error bars, right? So what we're going to do, as you can imagine, is use this information up here where it says average sorbed and average equilibrium solution concentration to visualize what the data look like in terms of typical sorption isotherm data, okay? So I think what we should do, though, first of all, is let's change this to CEQ, that variable there. And the units are going to be millimoles per liter. So what we're going to do together then is exclude row 1, okay, and select the data from column A, row 2, all the way to column E, row 28. And then we're just going to plot it. All right. So with it selected, we're going to plot it. So we're going to insert and we're going to create a scatter plot with connecting lines. And you can go to recommended charts. That might be an easier way to do it or the easiest way to do it. And then go to all charts. And the one that you want is scatter. And there's 2 choices that it'll give you by default. One is where the average sorbed is plotted on the x-axis, which is Q, and CEQ is plotted on the y-axis, which is opposite of what we want, right? So we want the second one, which is that one there, okay? So then we're going to click OK. Oh, wait. If you clicked OK, it's fine. But if you didn't click OK, click the scatter with smooth lines and markers. Right? Doesn't that look like L-type sorption? Yeah, nice. So then click OK. Yes. You have errors in your data. Well, Mia, maybe you shouldn't, right? It should be accurate. It should be correct if your formulas are correct. Well, so for some reason you only have 2. Oh, here's what I think is going on here. So maybe go back and if your sorption isotherm data look bad, go to the cadmium and lead worksheet and see if you have, I just want to get rid of that. Yeah, dang it.
Is your chart look different? I don't think so. I don't see it.
This is.
Yeah, I don't think mine looks.
All right, so for those of you whose data looks different, make sure that you have values for column D all the way down.
Or for C.
Yeah, so if you don't have them for column D, or the other one is, let's see, average solution. The other one that you need to have data for is column G. Should have data for column G all the way down. Okay, so probably you didn't fill down a formula for your Los Osos BTSS. So look at Los Osos BTSS and make sure that column I has data all the way down. If it doesn't, then maybe you didn't fill down all that data. And if column K doesn't have data all the way down, then make sure you fill those formulas down and then do the same thing for Holland BT.
What's the, okay, so,
It's the one where you're taking D2 minus I2 times 30 divided by E2.
right, would you?
Yeah.
And.
All right. You all good? Heck yeah. Yeah. Okay. So if we're going to create this chart, and are you all ready to do that again? I'll show you in just a second, Anna, but I'm just waiting for a couple people.
I have negative values.
Well,
Oh, wait, no, yeah. This is why I asked for 3 seconds. I knew I was gonna get something wrong. No. Can I see your values for the Los Lobos BTS SK? Just want to make sure that I have. Okay, cool. That should be it.
all right, we good? Sorption isotherm data. So we're going to start with cell A2, and we're selecting all the way over to cell E28, right? So you're not selecting row I, right? We're just selecting from A2 all the way over to E28. And then you're going to go to insert, and you go to recommended charts. Go to all charts. And then you want to go to scatter. You want the second option at the top that says scatter with smooth lines and markers. And the second option usually is the one that you want. And so once you have that, you just click OK. And my suggestion is that you take this and make it its own sheet. So I'm just going to right click on it and move the chart to a new sheet. And I'm going to call that sheet isotherm figure. You call it whatever you want. And then, of course, there's some things that you can do to make it look better, right? And I'll just show you a couple things that you can do to make it look better, and then I'll leave it on to your, time to make it better, because we still need to do some. What I want to do first of all, though, is, well, what we're going to do after this is do a Freundlich transformation of the data and a Langmuir transformation of the data. Okay. But what I want to do, first of all, is move the legend into my figure. And that comes from selecting it and then bringing it up there. And then I'm going to change how it is displayed, because it's easier when your data are displayed vertically for your legend to be displayed vertically also. You don't have to do that, but you should. All right. So then what I want to do, and this is helpful for any display of data, is that my legend entries here should match the order of my data. So I have Los Osos BTSS at the top. Then after that, I have Los Osos BTSS lead, and then Los Osos BTSS cadmium, and then Holland BT lead and Holland BT cadmium. And that's not how my legend is displayed. So I want to change the order of my legend. And the way to do that is to find any data point, right? Any one, doesn't matter, and select it, and then right click on it and go to select data. Okay, so all I did was selected a data point, well, not a single point, but select a data point. It should select a few different data points along your line there. And you can pick any line. I'm going to right click, go to select data, and I'm going to open up this window. And the first one that I want to display is Los Osos BTSS LED. So I'm going to click on that, and I'm going to do the up arrow to the top. And then I'm going to move Holland BT lead up above Holland BT cadmium, because that's how my data are displayed. And I can click OK. Right? Yep. That window. So if you hover over any of the data points and click on it, left click on it, and then right click on it, you should see this little menu that pops up and go to select data. Yeah. Okay. Another thing that we can do is we don't need our x-axis to go to -0.2, right? So what I want to do is format the x-axis. So I'm going to format the x-axis by clicking on it, and it'll select the x-axis in a rectangle. Then I'm going to right click there and go to format axis. And it'll say axis options, bounds, minimum and maximum. I'm just going to change my minimum to 0. And then if you still have that format axis open, if you click on the number here at the bottom, right, that's going to allow us to format the numbers a little differently. And it's displaying 3 decimal places, and we don't need 3 decimal places. We just need 1. So that'll take care of, if you click the add button at the bottom, that'll automatically change it right here and right now. So that did that pretty good. We could change for the y-axis, right? We don't need 2 decimal places here. So we can also get rid of those 2 decimal places and just put 0 decimal places and click add. And let's see, if you go to the plus sign up here for chart elements, we're missing some axis labels or some axis titles. So if I click on the plus and go to axis titles, just check that box. Then I can, you'll get an option to put in some axis titles. And if you click in there, your cursor will start blinking. And you can put in what that should be and what should it be for my y-axis. Q in what units? Millimoles per kilogram, right? My x-axis should be CEQ. So if you go to the, hang on, let me finish this and I'll show you. If you go here to this plus sign, and we don't need the grid lines either, right? So if you just select one of them, you'll see these little blue dots, and that means they're selected. So you just hit the delete, and same with the horizontal ones. You don't need those either. All right. So yeah.
You need a chart title.
No, you don't need a chart title. If you need to do anything with this, you can create a caption, right? That fits it. I would also like change the font color to black. And a way to do that is just to select it and then go to the home menu and you can make it bold and make the font color black and maybe make it bigger. Right, so it's just like you're formatting text in a Word document. You do the same thing, right? You just select it, go to the home menu, and then adjust the font like that. All right, what do the data show us? Lozo's BTSS sorbs the most lead and also the most cadmium, right? And it sorbs more lead and cadmium by quite a bit. But what about, is there some relationship between how the two soils sorb lead and cadmium? Yeah, lead always sorbs more than cadmium, independent of soil type, right? So the soils, right, are different in terms of how much metal they retain, but there's similarity in the metal that they exhibit some preference for, right, in terms of the ability of the BT and BTSS horizons to retain the lead and cadmium. So we'll talk about why that is later, but you probably already know why that is. All right, so what I would, if I was working with this, what I would do is I'd make the fonts a little bit bigger on my axes, make my title different or bold and bigger, stuff like that. So let's go to the Freundlich data. Okay, so the Freundlich data is a log transformation. And so all this on this spreadsheet is in columns A through E. It's just copying the data that we had in the isotherm worksheet. So same stuff. And then over from there, starting column G, it's just taking the log of that first column and then the log of columns B, C, D, and E, right? Because the plot for the linear transformation of Freundlich is log Q on the y-axis and log C EQ on the x-axis, right? So that's just been done for us here, right? All the way across here. So what that should mean is that now the data have been transformed into a linear format or into a format that says y equals mx plus b. We do have this one value that says hashtag number, right? Any of you do that one? Ready? Hashtag number. Yeah. No. Okay. So that is the one that we got rid of before, right? That was an outlier. So we're just going to delete it. So then we're going to plot this again, but we're going to start in column or in cell G2 and select all the way over to K24, G2 to K24. All right, and then do the same thing. This time we're going to do a scatter. And after we do the scatter, we're going to add a trend line to it. And we're going to have Excel plot up an equation for the line and calculate an R squared for that line. So it's the same as before. Insert recommended charts. You can do that one and go to all charts. You can go to scatter, and I would just pick the one on the right and go to OK. And then again, move this to its own worksheet. And you could call this one like Freundlich figure. Okay, so here is where we'll select our first data set. And I'm going to select the Los Osos BTSS lead, which are the green ones. I'm going to click on it once. And then, let's see here. What happens if I right click? Oh, so you click on it. And then if you right click on it, you can add a trend line. Do that, and you open up the format trend line option. And that allows you to display an equation on the chart and display an R square value also. Okay, so you just do that for all of them, right? All the lines.
And do you still want grid line?
You can get rid of those grid lines. It is hard to move those boxes. But I would encourage you to do it because if you leave them where it puts it by default, it's hard to know which is which.
Mm.
All right, I got a couple of suggestions kind of off the bat is to move the y-axis over to -3. So it's on the far left. And to make your x-axis end at 0. Okay, so let's talk about how to do that. If you select your y-axis values and then right click on it, you can go to Format Axis and it'll say horizontal line crosses at, and you can put in a value. And we want that to be -3 instead of 0. Yeah, yeah, -3.0. It's good. Should move it. I think I did it wrong. Yes. Did it at the wrong one. Thank you. Yeah, so do it on the x-axis. And right click there, Format Axis. And go to axis value -3. Go. And then of course you're missing your axis labels or axis titles, so you need to put those in. And on your y-axis, it's log Q, and your x-axis is log C. And then you got all this stuff at the bottom. All right, you all know what to do, like to make it look better, but I'm gonna make a couple more suggestions. And those couple more suggestions is in the legend, we need to change the order. You know how to do that, but we don't need the parts that say linear, right? We don't need the legend entries that say linear. So if you double click on those, you'll select them and you can just delete it. So when you select it, you'll see 4 blue dots around it. And if you just hit your delete, you get rid of it. So if you like double click on a legend entry, and then you just hit delete if you don't want it.
What's happening? But it's not usually possible. I'm going to mystery portrait that one for sure. Yes. It's all the same.
Totally. Learning.
I would have had a mental breakdown.
All right, before we go to the next thing, which is just doing the Langmuir one, what I'd like you to do for each of the soils and metals is to calculate KD. All right, you can do it. So find out what KD is for each of them before you move to, before we move on to the Langmuir. And what I think is that take a stab at making the Langmuir graph based upon the data there. It's very similar to what we just did. Bless you. All right, you probably did it already, but I am going to talk about making the Langmuir figure. And the data are displayed exactly the same, but this time the y-axis is CEQ over Q. Sorry, yeah, that's right. The y-axis is CEQ over Q, and the x-axis is still CEQ. And so the data that you need to select go from cell G2 to K24, probably, yeah, K24. And then you just plot it the same way, scatter, and then add trend lines. and put in the same information that you did, right? You put in some axis titles, transform it as you need to transform it.
And then just put it through the scene border. Just combine this.
And then once you have the Langmuir figure plotted linearly, what do we want to solve for that? Qmax. So solve for Qmax.